So our next iterative method, so Jacobi method. Jacobi method, also known as Gauss-Jacobi method, is one of the most common iterative methods in solving linear system. In this method, the equation of the system will be transformed in the form of this particular equation. And assuming all a sub ij is equals to 0, initially values of x are substituted simultaneously, and this process is repeated until a certain accuracy of the value is achieved. However, this method is very restrictive because this requires that the coefficient of matrix A is diagonally dominant. That it must satisfy the coefficient of matrix A is greater than the summation of A sub ij. So, in connection with this are the step-by-step procedure to perform Jacobi method in linear system. So, first, we need to check if the system is diagonally dominant. So, to check for the three-equation linear system, so we must check that A sub 1, 1 is greater than A sub 1, 2 plus A sub 1, 3, and A sub 2, 2 is greater than A sub 2, 1 plus A sub 2, 3, and A sub 3, 3 is greater than A sub 3, 1 plus A sub 3, 2. For 4 equation of linear system, so there is a similarity, so there are just increase of the element to be summed up and to be compared if they are greater than to the diagonal values or to the diagonal elements of the matrix. So by intuition, the reader may establish checking of linear systems of n greater than 4 if the system is initially not diagonally dominant. Use other methods in solving the linear system. So for the next step, isolate x sub 1, x sub 2, so on and so forth until x sub n in equations 1, 2, and so on and so forth and value respectively. Third, set an initial value of x sub 1 to x sub n. Oftentimes, x sub 1 raised to 0 is equals to x sub 2 raised to 0 equals to so on and so forth, x sub n raised to 0 equals to 0. Fourth, solve for the new value of x sub 1 to x sub n by substituting the initial values of them simultaneously in the equation generated from step 2. Repeat the process several times until a certain accuracy of the value is achieved. So note, tabular representation of each iteration is recommended to show how the value of x converge. So the coefficient of matrix A must be diagonally dominant because if it's not, the value of x will diverge and this method cannot solve the system. So in order to really understand how Jacobi method is applied or how it is used, so first for a problem statement, so determine the solution of linear system shown below using Jacobi method. So we will use here the same equation we used to other methods applied. So for the solution, first we need to check if the system is diagonally dominant. So you will compare. These are the diagonal. So these are the diagonal values of the matrix. So we have here, we will compare here if 3 is greater than to the summation of the other coefficients. Same with 7 to the coefficient of 0.1 and 0.3 and 10 to the coefficient of 0.3 and negative 0.2. So you will notice here they are all diagonally dominant. So we will now be able to apply Jacobi method since we have already checked if the system is diagonally dominant. So in continuation of the solution, we're going to isolate x sub 1, x sub 2, and until x sub n in equations 1, 2, and so on and so forth respectively. So we used equation 1 in finding x sub 1 and we used our equation 2 in finding x sub 2. We used equation 3 in finding x sub 3. So we used the equations with a dominance value. This is the coefficient of x sub 1. This is the coefficient of x sub 2 and this is the coefficient of x sub 3 from the given equation. Our problem only has 3 linear equations. So, until x sub 3 only. So, continuation of solution, set an initial value of x sub 1 to x sub n. Oftentimes, x sub 1, so it will start at 0 with all the values equated to 0. So, x sub 1 is 0, x sub 2 is 0, x sub n is 0. Then, substitute this value to the equation above to perform the first iteration. Note that the 0 raised in variable x indicates the iteration, and that is not an exponent. So we will have here the value. So this is the value for our x sub 1, x sub 2, and x sub 3. And this is for our first iteration. So it is also noted that we should use a tabular representation in order to clearly understand how the solution process goes. So continuing the solution, so repeat the process until it will give you this representation or tabular representation. So also in here, upon calculating the value of x sub 1, x sub 2, and x sub 3 are also going to calculate the approximation percent relative error and the true percent relative error. So, for all the values of x sub 1, x sub 2, x sub 3. So, we'll try this using Excel. First, on our process, so this is the first step. This is checking if our diagonal values of our equation is dominant. So we have here, based on our previous calculation, so we have the values of the true value of our x sub 1, x sub 2, and x sub 3. And class, take note, in applying the first step, which is checking whether the system is diagonally dominant, class, we're going to use the absolute values of each coefficient. So, for example, we're going to check if 3 is dominant to our equation. So, what we're going to use is to calculate 0.1 plus 0.2. And similar, so 0.1 plus 0.3. So, this will be 0.4. And for our 10, so this is similarly 0.3 plus 0.2. They were all dominant. So, and using the equation 1, with a dominant value. So, we're going to use x sub 1, so for x sub 2, and for our x sub 3. So, these are all the separations. So, we separate the x sub 1, x sub 2, and x sub 3 of the equations 1, 2, and 3. So, how are we going to calculate? Upon isolation, so what we're going to have here is to set an initial value of x sub 1 to x sub n. So, we need to set an initial values of 0 for all the x values. Next, we're going to calculate for the first iteration. Our first iteration, class, it will involve for our x sub 1 over 3 multiplied by 7.85 plus 0.1 multiplied by x sub 0, so the initial, so from the previous, plus 0.2 times x sub 3. And we will be able here to find the value of 2.6166 so on and so forth. For our x sub 2, so this will be 1 over 7 multiplied by value of 19.3 minus 0.1 multiplied by x sub 1, so the previous value, plus 0.3 times x sub 3. So, we will be able to calculate negative 2.7571. So, for x sub 3, using the third equation, so 1 over 10 times 71.4 minus 0.3 times x sub 1 plus 0.2 times x sub 2. So, nawala tayo ng product. So, ayun. So, we will be able to have here the value of 7.14. So, same process. So, let's copy this out, class. So, you will notice here, so same process, 1 over 3 multiplied by 7.85 times 0.1, class. You will not be using the 0. So, you will now use the value at the first iteration. Same with x sub 3. So, this will be the value. And for our x sub 2, same process. So, hindi na yung 0 ang ginamit for the values. And also, for this x sub 3. So, ang ginamit na natin is the value at the first iteration. So, copying it out, class. So, for the third iteration, we use now the second iteration for x sub 2. The second iteration for x sub 3. Similar here. So, similar with these two. So, copying it out, we'll be able to have here, at the 8th iteration, we were able to find the value of x sub 1, x sub 2, and x sub 3. So, we're now going to calculate for the approximation percent relative error for each values of x. So, this is simply current minus previous divided by the current multiplied by 100. So, just simply copy paste. So, just recheck if you copied it right. So, for true value or true percent relative error, so what we're going to do is to define the true value first. So, for x sub 1, so for Jacobi. So, for x sub 2, so for Jacobi. And for x sub 3, so that we will not change the selected cell that easily. So, for the true value, so simply x sub 1 underscore minus approximation divided by x sub 1, so times 100. So we have here an error. So let's copy it out. So let's just change this to 2 and also this to 2 for the x sub 2 and also this for 3 for x sub 3 and also this for 3 for x sub 3. And simply copy it out. This is the value of 1 equals to 3, x sub 2 equals to negative 2.5, and x sub 3 equals to 7. So this is using Excel, applying Jacobi method. Our next discussion will be about Gauss-Seidel method. So, Gauss-Seidel method, also known as the successive displacement method, is considered an improvement of Jacobi method. So, the Gauss-Seidel method is the most commonly used iterative method. Assume that we are given a set of n equations. So, this is the matrix form of the linear equation. Suppose that the conciseness will limit ourselves to a 3 by 3 set of equations. If the diagonal elements are all non-zero, the first equation can be solved for x sub 1, the second for x sub 2, and the third for x sub 3 to yield the given equation. So after this, we can now start the solution process by choosing guesses for the x. So a simple way of obtaining initial guesses is to assume that they are 0. These zeros can be substituted to the equations 11.5a to 11.5c. Then we return to the first equation and repeat the entire procedure until our solution converges closely enough to the true value. So convergence can be checked using the criterion. So, in order to understand the solution process or how the method is applied, so for example, the problem statement used the Gauss-Seidel method to obtain the solution of the same system. So, we will also have here the same system we used applying Jacobi method. So, recall that the true values are x sub 1 equals to 3, x sub 2 equals to negative 2.5, and x sub 3 equals to 7. So, this is the solution. First, solve each of the equation for its unknown on the diagonal. So, by assuming that x sub 2 and x sub 3 are 0, we will be able to calculate x sub 1. So, the value of x sub 1 along with the value of x sub 3 as 0, we will be able to substitute it to this particular equation and getting the value of x sub 2. And for next process, so the first iteration is completed by substituting the calculated values for x sub 1 and x sub 2 into the given equation. So we have here, instead of using the 0 values, we're now going to use the value calculated for x sub 1 and x sub 2 in order to calculate the value of x sub 3. And for the second iteration, same process is repeated to calculate this particular equation with its true percent relative errors of 0.31, 0.015, and 0.0042% respectively. So, this method is therefore converging to the true solution. Additional iterations could be applied to improve the answers. However, in an actual problem, we would not know the true answer a priori. Consequently, for this equation, we will be able to provide a means to estimate the error. So, for our approximation percent relative error, for x sub 1, we will have here 12.5. For our x sub 2, 11.8. And for our x sub 3, 0.076. So, note that, as was the case when determining roots of single equation, formulation usually provide a conservative appraisal of convergence. Thus, when they are met, they ensure that the result is known to at least tolerance specified by epsilon sub s or the pre-specified acceptable criterion or error. And this solution process can be tabulated in this particular sequence. So we're going to use Excel applying Gauss-Seidel method. Upon applying Gauss-Seidel method, it is still better to check whether the linear system is diagonally dominant or not. And if not, you can rearrange the sequencing of your linear equations to satisfy the first step, which is checking whether the linear system is diagonally dominant. So if the system is diagonally dominant, so similarly, we will use the same equation with Jacobi method. Second step is also similar. So set the values for the initial as 0 and for the iteration. So for our x sub 1, going to use the equation. So they are the same. And 7.85 plus 0.1 multiplied by x sub 2. So x sub 2 is the value at the previous iteration plus for the x sub 3 multiplied by the values x sub 3. And they will have the value of x sub 1, 2.616666, so on and so forth. For x sub 2, the difference of Gauss-Seidel method to the Jacobi method is Gauss-Seidel method. So for the equation, 1 over 7 multiplied by negative 19.30 minus 0.1. For our x sub 1, so on our Jacobi method, we selected the value of x sub 1 at the first iteration. So its difference to Gauss-Seidel, Gauss-Seidel uses the resulted or the new value of the x sub 1 plus 0.30 multiplied by x sub 3, which is still the value equal to 0. And for x sub 3, 1 over 10 multiplied by 71.4 minus 0.3 times x sub 1. So the x sub 1 is based on the first iteration already, plus 0.2 times the new calculated value of x sub 2 on the first iteration. So we will be able to get these particular values. So similarly, so let's copy this out. So for our x sub 1, so we're going to use the x sub 2 and x sub 3 of the first iteration based on the substitution based on the equation. And we will be able to find this equation. And for our second iteration for x sub 2, so we are going to use calculated value of x sub 1 on the second iteration. And instead of using x sub 3 on the 0 iteration, we're going to use the value of x sub 3 at the first iteration. And for the x sub 3 at the second iteration, we're now going to use the value of x sub 1 at the second iteration and x sub 2 at the second iteration. So, copy. So, we will be able to get these particular values. So, we will not have a value of approximation, percent relative error on the first because we still don't have the previous approximation. So, on the first iteration, current minus previous divided by current multiplied by 100. So, similar process will be used. So, we will be able to have this percent relative error based on the approximation. And based on the true value, so we can define these values as x sub 1 for our Gauss-Seidel. And also this value, let's define this as x sub 2, and we'll also define this as x sub 3. So, for the true value, so x sub 1 minus the value divided by the true value times 100. So, it has an error of 100. So, let's change this to 2 and also this to 2 for x sub 2 and also this for x sub 3. Also this for x sub 3. And so same process will be applied. So you can just simply check whether the selected cells are all correct. On the 10th iteration, you will notice that based on Excel calculation, they already represented that the values of x sub 1, x sub 2, and x sub 3 has negligible error or zero error based on approximation and true value. So, mas concise or mas maiksi ang calculation ni Gauss-Seidel compared kay Jacobi. Even though they use the same equations based on the system's diagonal dominance. We already use Excel in applying Gauss-Seidel method and it is also represented in this similar tabulation. So that would be all our discussion about solving systems of linear equations. So hope you are following all our discussions and lessons. So thank you so much. Have a great day ahead and please study our lesson. Thank you.